Okay, IB topic 2.2, electron configurations. Now today our focus will be on the nature of light and the Bohr model of the atom. It won't be until next time that we actually look at electron configurations. Okay, let's look at light.
Visible light is a form of electromagnetic radiation, which emanates from the source as waves. The waves are electric and magnetic fields oriented perpendicular to each other.
Okay, so what we're going to be interested in for a little while here is the nature of light and the information that we can derive from looking at it very, very carefully. The electromagnetic spectrum. Okay, here you see it being represented by a change in wavelength. You see that the wavelengths get smaller and smaller, and the portions of the electromagnetic spectrum that you were responsible for that exist: radio waves, then microwaves, infrared, visible light, you can see it's blown up here, and then ultraviolet, X-rays, gamma rays. On the left side, the wavelengths are longer wavelengths, lower frequency, lower energy. Frequency is the number of waves that pass a given point over a certain amount of time. So over on the left here, long wavelengths, low frequency, low energy. On the other side, just the opposite. The wavelengths get shorter and shorter, high frequency, high energy. Now, the visible portion of the spectrum is blown up here. You can see the colors, all the colors of the rainbow, which you can easily remember using this little acronym Roy G. Biv. If you're not familiar with it, it's a pretty handy thing to know. It stands for red, orange, yellow, green, blue, indigo, violet, all the colors of the rainbow. Now, on the left side here, this portion of the electromagnetic spectrum, including visible light, are very low energy, are not dangerous, which kind of surprised students when they see microwaves over here, because of course we associate microwaves with microwaves oven, which are dangerous. But in microwave ovens, they take microwaves and concentrate it into a small area, and so you have a concentration of microwaves. And you might be familiar with doing this with the visible light. If you take a magnifying glass, take it outside, and focus the light that strikes the magnifying glass into a point, you can light a piece of paper on fire or maybe torture a bug or something like that. So it's not that the light itself is dangerous, but we can concentrate it. And so that's what happens inside a microwave oven. We concentrate the microwaves. And the microwave, the wavelength is just right to cause the water molecule to spin around. And when the water molecules spin around, whatever medium they're in will cause it to warm up, just like rubbing your hands together gets warm. On the right side, these are very dangerous. Ultraviolet light we associate with skin cancer, sunburns, X-rays, gamma rays. These are all very dangerous. There's an IB video that you can go to and watch more about it. Remember, just go to tutorials, IB videos, and you want section 2.2. This again is the electromagnetic spectrum, and these two opposing arrows give us different information. As we go from the left to the right on the top here, going from radio waves all the way to gamma rays, we have an increase in frequency and an increase in energy. Going in the opposite direction, we have an increase in wavelength. So you can see that. Where does electromagnetic radiation come from? All electromagnetic radiation comes from the movement of electrons or other charged particles. If an electron or a charged particle moves, what it moves along with it is what we call its electric field lines. Let's take a look at that. So here we have an electron. Now it has a negative charge. If I was to bring something, let's say another electron close to it, well, they're going to repel each other. Like charges repel each other. It doesn't matter from where the electron comes, it's going to be repelled. So we can use these arrows to represent that force, that negative force that emanates in all directions. We call those, or we can represent those by what we call electric field lines. Like field, just like a field of grass. So you have these electric field lines emanating in all directions. Let's take a look at just one of those field lines. And let's bring it down here. So we just have the electron and one of those electric field lines. Well, what would happen if I was to take that electron and move it up and down, up and down? Well, as you might suspect, that electric field line would move along with it. So we can see that taking place here. Now, I know that you've already drawn some of this in your notes, so right now you can draw that wavelength, or the wave that's emanating as the electron goes up and down. The distance between two crests is referred to as the wavelength. You can see that the wavelength remains constant as long as the movement of the electron is constant. Now, when an electron transmits energy through space, all that it's doing is transmitting that energy via its electric field line. So imagine that this was a rope, and you were holding one end, let's say over here, and another person was holding over here. Well, if that person starts moving it up and down really fast, of course, that energy would transfer over, and you would feel the rope, a lot of energy coming your way. Whereas if that person slowed down, be less energy, and less energy would make it over to you. So it's exactly the same thing with electromagnetic radiation. The more the electron is moving, the faster that it's moving, the more energy it's going to transmit. All right, let's look at a wave in greater detail. When we draw a wave, the highest point is referred to as the crest. The lowest point is referred to as a trough. The distance between one crest and the next, or it could be between one trough and the next, is referred to as the wavelength. And we use the Greek letter lambda to represent that. Kind of looks like an upside down italic Y. That's a wavelength. The height of the wave is called its amplitude. The number of waves that pass a given point over a period of time is called its frequency. If you have one wave pass a certain point every second, then we say that the wavelength's frequency, or the wave's frequency, is 1 hertz. So if you had, say, 10 waves pass a given point in 1 second, it would have the frequency of 10 hertz. We use the Greek letter nu to represent frequency, which kind of looks like an italic V. In recent years, it seems like the symbol nu has lost favor, and often you'll just see a capital F representing frequency, though lambda still is hanging in there. A little trivia here, you know that there is AM radios and FM radios. Well, an AM radio reads a modulate, and it's AM, amplitude modulation, which means changing. So we change the amplitude, your radios, AM radios, tune in to that change in amplitude. FM radios is frequency modulation. So they change the frequency of the wave, and that's what your radio tunes into. The speed of a wave is always the product of wavelength times frequency. Multiply those two together, and you would get the speed of a wave. Now, all light travels, and this is a constant of nature, travels at 300,000 kilometers per second, or 186,000 miles per second. We use a lowercase c to represent the speed of light. So the speed of light can be determined by multiplying the wavelength and the frequency. So in previous slides, we looked at how frequency changes, then wavelength changes, and vice versa. So lambda and frequency are inversely proportional, meaning as one gets larger, the other gets smaller. And that's why the product of the two will give you a constant value. If the wavelength gets larger, then the frequency would get smaller, and vice versa. Always giving you a constant value of 300,000 kilometers per second. This is a little animation that you can play around with. I'll put a link in today's lesson file, and you can play around with this little simulation where you can change the amplitude, you can change the frequency, and see how it changes the wavelength. A continuous spectrum contains all wavelengths of light. So when we talk about a continuous spectrum, it's always just visible light, all the colors, Roy G. Biv. But an emission or line spectrum contains only certain wavelengths of light, where all the other colors are missing. Here's a little animation on exactly what's going on there.
Late 19th century, scientists observed that a characteristic lavender light was produced when a high-voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors.
And the lavender light that she's referring to here is hydrogen. You might remember the emission spectrum lab that you did last year had different glass tubes that electricity was being passed through and it produced light. One of them was a lavender color, and that was the unknown, you might remember, and that was hydrogen. Every element emits its own unique emission spectrum that can be used to identify it. So sodium would give off these lines, hydrogen these, calcium these, mercury these, etc. This is how we can look at the stars, say, and know what they're made of, because we can pass the light through a spectroscope and analyze it and identify the elements from which it must be made. We can do that with the planets, with the moon, anything that gives off light, we can analyze it using a spectroscope. Although emission spectra was easily observed, no one could explain why atoms did this. We're talking about the end of the 19th century, early 20th century. Enter our hero of the day, Niels Bohr. The Bohr model of the hydrogen atom. Niels Bohr, 1885 to 1962, Danish physicist, Nobel laureate. Element 107 was named in his honor, bohrium. Just an amazing, amazing man. He was a contemporary of Einstein, and they were very well acquainted with one another. They often argued back and forth with different ideas, but he was just an amazing man. In 1912, Niels Bohr devised a theory that explained both emission spectra and how electrons move within an atom. Another video that you could look at in the tutorials to a lot more about Niels Bohr in those videos and his model. All right, now let's look at his model. Bohr's theory stated that electrons could only exist within allowed orbits that he called energy levels. And so here we have the nucleus, and each one of these circles represents one of these, what he called allowed energy levels or orbits. So here we have an electron in this energy level, electron here, electron here. So as long as the electrons were in those energy levels, again, the energy levels you can just think of as an orbit, everything was fine. They were happy. But between these energy levels, electrons could not exist. And this was a very strange idea. Why couldn't the electron be anywhere, any distance at all? It didn't seem to make any sense. But using this idea, Bohr was able to explain the emission spectra of the lines. If the electrons could be any distance, as we'll see, then every atom would give off a continuous spectrum, would give off all colors. But because the electrons can only exist at allowed energy levels, that explained why every element gives off a unique series of emission lines. Now we can understand this if we look at what's called the wave nature of the electron. An allowed energy level is most easily understood if an electron is thought of as a wave moving around the nucleus. Now, when you have something that has mass and it's moving, it will always move in a wave, as a wave. The larger something is, the smaller the wavelength is. So you and I, when we move around, our wavelength is so insanely small that it can never ever be measured. but the electron is small enough that we can measure its wavelength as it moves around. These are called de Broglie waves or matter waves. Louis de Broglie, 1892 to 1987, also a Nobel laureate. Now, what's of interest here is notice that the wave begins and ends at the same point. So any point that you draw on the energy level, the wave doesn't rotate around. It remains in sync with itself, as we'll see here in a second. Within each one of these energy levels, the wave arrives right where it started from. So when you draw these in your notes, try to draw a wave that wherever you start the wave as it goes around, have it end at that same point. Let's say what I have right here, my cursor right there. So you can see that point is the same. And you can just freeze or stop the video and just draw the wave that you're looking at. If an electron wave overlaps, it is in phase with itself. You can see that here. Anywhere in between the energy levels, an electron wave will interfere with itself and cancel out. And that's what we have going on here. It is out of phase. Now, a real-world experience you may have had, if you were in a swimming pool, say, and you were having kind of a water fight with another person, you're splashing waves in their direction and they're splashing waves in your direction, you may have noticed that when the waves hit one another, they cancel each other out. And the wave that the other person's trying to get to you may never arrive, and vice versa. And that's because they're out of sync with one another. They're out of phase with one another. They cancel each other out. And so the same thing occurs if an electron tries to exist at any location other than an allowed energy level. It will cancel itself out. Let me go back for 1 second. I think I forgot to point something out. I did. The number of nodes, which are the crests of the wave, corresponds to what energy level it's at. So if you were to count the number of and now the animation I'm using here probably doesn't fit that as well, but let's say the first energy level would have 4 nodes, the second would have 5, the third would have 6. So I'm not quite exactly sure of what the numbers are, but you would have a different number of waves in each one of those energy levels. Now, if you're interested in this, and it's really quite fascinating, I'll put a link to this video in today's lesson file page. Remember, at the end of every day, if I have some links or keys or something to share with you, I'll include those. And so I'll include a link to this video, which is really quite good. Now let's look at the Bohr model of the hydrogen atom. Now, why the hydrogen atom? Because it has only 1 electron, and so it's really it's the simplest of all atoms, and so that's the one that we can kind of understand the easiest, and the one that Bohr used first. So each one of these circles represents one of the allowed energy levels. Again, just think of it as orbits. Each one is numbered. N equals 1 is the first energy level, N equals 2 the second, etc. It goes all the way to infinity, theoretically. Note, as N increases, the energy levels get closer together. This is called convergence. So you can see the the orbits get closer and closer and closer together. So here we have 1 electron is in the second energy level. If we energize it, it will go up to a higher energy level. And in order for that to happen, it would have to absorb energy. Energy would have to go into it, like throwing a ball up in the air. Now, the electron is negatively charged, the nucleus is positively charged. So to move the electron away from the nucleus, you would have to put energy in. Well, just like throwing a ball up in the air, the electron's going to want to fall back down. It's attracted to the nucleus. And when it falls back down, it will give off energy, exactly the amount of energy that relates to the difference between these 2 energy levels. When it falls back down, it'll give off energy in the form of electromagnetic radiation. And in this case, in this specific transition, it'll give off blue light. Here, green light. here, red light. All right, now, I think in your pre-notes I told you not to worry about copying this diagram, but this one I hope you copied down. So this is exactly the same thing. It's just a little bit easier to interpret. So we have the nucleus at the bottom here, and the energy levels numbered all the way to infinity. Higher energy is going towards infinity. Lower energy is going towards the first energy level. Now, the electron would never be able to be below the first energy level. This is no man's land for an electron. So let's look at the transition of an electron going from the second energy level to the fifth and back down again. Again, the energy that's given off is only when it comes back down. And for this particular transition, from going from 5 back down to 2 gives off blue light. Going from 4 back down to 2 gives off green, and 3 back down to 2 gives off red. Notice the change in energy we can denote by the size of the wavelength. So blue light has higher energy than red light, so the wavelengths would be shorter than red, and green would be intermediate. More energy, less energy. Okay, this is the same diagram shown again. This is the emission spectrum that we would see for the hydrogen atom. And notice that the lines get closer and closer together. And that comes from the convergence of the energy levels. Energy increases, in this case, as we go from the left to right. A question that I will often ask on the test is, I'll give you a box, a rectangle like this, and I'll ask you to draw 4 lines that represent the convergence of the spectral lines. And all you would need to do is draw 4 lines, making sure that that each line that you draw is closer and closer to the one right before it. So greatest distance between the first 2, and then the distance decreases, decreases. And if I ask you to draw a 5, the other one would be like right here. They just get closer and closer together. Just make sure that the lines get closer together in the direction that energy increases. Sometimes I fake you out and I have the arrow pointing in the opposite direction, energy increases. And so everything would be flipped in that case. As energy increases, the spectral lines converge, get closer together. Now, there are 3 sets of emission lines that you need to know. The first, infrared radiation, this is called the Paschen lines or Paschen series. This is when the electrons transition down to the 3rd energy level. It doesn't matter from where they came, but if they transition down to the 3rd energy level, they're going to give off infrared radiation, Paschen lines or Paschen series. If they come down to the 2nd energy level, that's visible light, and we call that Balmer lines or Balmer series. And the transition that we saw before, going from the 3rd to the 2nd, is red light, from the 4th to the 2nd, green, 5th to the 2nd, blue, and 6th to the 2nd would be violet. And then if the transitions came down to the 1st energy level, this is not the nucleus, this is the 1st energy level, those are called Lyman lines or the Lyman series, ultraviolet radiation in that case. Okay, let's summarize the Bohr model. Electrons orbit the nucleus only within allowed energy levels. Each energy level is at a specific distance from the nucleus. Within an energy level, electrons do not lose energy. And this was the big problem with Rutherford's model of the atom. He had discovered the nucleus, but he had the electrons going around the nucleus like a planet around the sun. Now, he knew, as well as everybody else, scientists of the day, that that couldn't be, because the electron, a charged particle traveling in a circular path like that, what's called angular acceleration, would lose energy and should quickly spiral and collapse into the nucleus. But with the idea of allowed energy levels, where the electron wave superimposes on itself, doesn't cancel itself out, it can exist without losing energy. And so that problem was solved. When electrons are in the lowest energy levels available, the atom, not the electron, but the atom having that electron is said to be in the ground state. So here I have two energy levels, and you see the electron is at the lower one, so it's in the ground state. When electrons absorb energy and move to a higher energy level, the atom is in an excited state. So here the electron has been elevated up to a higher energy level. When an electron returns to a lower energy level, it will give off electromagnetic radiation with energy exactly equal to the difference found between those energy levels. And this was the big insight that Bohr had, that we could explain the emission lines using the idea of allowed energy levels. Okay, now we've already seen this diagram before, but let me just kind of make a point here before we say goodbye. This is the continuous spectrum, and these are the emission spectrum that we would see for these elements listed. If allowed energy levels were not the case, if an electron could be at any orbit it wanted to around the nucleus, that means it could transition from anywhere to anywhere, which means that all types of energy would be given off. And if we were to look at just the visible portion of the electromagnetic spectrum, that would mean that all elements would give off a continuous spectrum because all transitions were possible. But that's not what we saw. That's not what Bohr saw. That's not what anyone saw. Every element gave off its own unique patterns of light. So it must mean that the electrons could be at only allowed energy levels. Okay, that is the end of today's notes.